Hi everyone, I'm Hao Guo from Tsinghua University. Today, I'll introduce my colleague Ruwen's work, GPREEMPT, GPU preemptive scheduling made general and efficient. This is a joint work with Tingxu, Minhui, Shiwei, Professor Jiwu, and Professor Youyou. GPUs are widely used in many computing tasks, such as computer vision, machine learning, and graph computing. These tasks often have diverse service level agreement requirements, or SLA. We can categorize them into two main types: latency-critical or LC applications like real-time recommendation and autonomous driving, and best-effort workloads or BE workloads like offline inference. These workloads often fluctuate during days, leading to periods of low traffic. For example, this is a statistic from Microsoft showing the peak and off hour of the model serving. Statically dedicating the GPU to a single task is inefficient, causing significant resource wastage. Leveraging the various SLA requirements of the tasks, co-locating multiple tasks on GPU is a good way to improve utilization. However, co-location introduces a critical challenge. BE tasks cannot interfere with LC tasks, potentially violating their SLA guarantees. For example, if we place tasks in different streams within the same context, as the stream provides no preemption guarantee, an LC kernel can get blocked by a long-running BE kernel. Or, if we use different contexts to execute the tasks, the GPU scheduler simply time slices between them. An LC task's execution can be fragmented, delaying its completion. Furthermore, the GPU programming model is not designed for fine-grained scheduling. Let's quickly review a GPU kernel. A GPU kernel consists of many thread blocks, with each of which contains multiple threads. We launch a kernel, specifying the number of blocks and threads. Usually, the execution unit in the GPU is smaller than the numbers of the kernel. These blocks execute on the execution units in waves. The host program calls a synchronize function and simply waits. It only returns after all the blocks have finished. This launch and wait model offers no control to the developer once the kernel is running. Existing works have also attempted to preempt tasks on GPU to ensure the SLA of LC tasks. They can be roughly divided into two categories. The first is wait-based approach. A typical method is to sequentially execute each kernel, check before launching each kernel. However, if the GPU is currently executing a kernel, the LC task must wait for the running kernel. And, as we have introduced just now, kernels are executed on the GPU in waves. So another way is to modify the kernel code is to check if there is an LC task before each block is executed. When LC arrives, the blocks exit directly. This makes the preemption latency become the execution length of a block. The other is the reset-based approach. They directly kill the running BE kernel on the GPU. This requires that these GPU kernels are idempotent. That is, the results generated with the same input are always the same. In this way, tasks can be terminated at any time, which makes the preemption latency almost zero. However, existing solutions force us into a difficult trade-off. The wait-based approach is general but inefficient, which often faces with high latency. As the following figure shows, we co-locate LC tasks with BE tasks. The wait-based approach incurs high latency, while the reset-based approach is efficient but not general, limiting its application. For example, a workload contains no idempotent kernel is not applicable. This leads to our key question: can we achieve both generality and efficiency? To be applicable to non-idempotent tasks, we shouldn't drop the BE task state. To keep a stable preemption latency, we cannot wait for kernels or blocks to finish. Taking inspiration from operating systems, the ideal solution is context switch. The OS can save a task state, switch to another, and restore the original task later. This is both general and efficient. However, this cannot be easily migrated to GPU. When we use the GPUs, from a programmer's perspective, we just launch kernels and synchronize to complete. The GPU runtime provides no scheduling interface. When a kernel launches, the GPU is just like a black box, which provides no scheduling interface to us. In fact, GPU provides the context switch with a hardware scheduling way. When two different tasks run on the same GPU, the GPU runs two tasks in a time-slice round-robin manner. When there are only one task, the GPU will continually run it. From this, we can see context switch is an inherent feature in the GPU, which can be leveraged to preempt the task. This insight is the core of GPREEMPT. Although we cannot actively initiate a context switch, we can trigger it indirectly. We propose time slice-based preemption. Leveraging the existing switch mechanism, we repurpose it into preemption by adjusting the time slice. We can shrink the BE task time slice to near zero and expand the LC task slice to be effectively infinite. When the LC kernel launches, the BE task will almost immediately yield to it, and the LC task will run to completion without being interfered with. And after a detailed analysis and modification of the GPU open source driver, we modify the API and expose it as a simple priority setting API to users. The switch itself is performed in hardware, adding no software overhead. And adjusting time slice requires no modification to the kernel code, which is transparent to existing kernels. However, this hardware preemption is not free. There is still overhead. First, there is a minimum time slice. On an NVIDIA A100, it's about 200 microseconds. An arriving LC task may have to wait for the remainder of the BE task current time slice, which is 100 microseconds on average. Second, the context itself must be saved. The A100's compute context is 44 megabytes, and the HBM bandwidth is only 1.1 terabytes per second. Saving it takes another 40 microseconds. In total, we face a preemption latency of about 140 microseconds. Let's come back to the GPU computing paradigm. How do we offload a task to GPU? Before a kernel can be launched, there is almost always a data preparation stage that involves pre-processing on the CPU, like image cropping, and then transferring the data to the GPU, which is typically done by the DIMA engine. This means there is a predictable delay between when we receive an LC task and when the LC kernel is already launched. So a timeline of the LC task is just like this. There will be a switch overhead between the copy stage and the kernel execution stage. Can we move forward the preemption stage as we already know the arrival of LC task? In this way, when the data is ready, the LC kernels can be directly run. The LC kernels cannot be launched until the data preparation. And as introduced, when only multiple tasks run together, the GPU will switch between them. So we just launch an empty kernel when the LC preparation stage starts and exit it when the data preparation finishes, just like this. But if we preempt in advance too much, the GPU will be idle for a long time, which hurts the throughput of BE tasks. So can we postpone the preemption a bit later? We use a background thread to launch the empty kernel. When LC tasks arrive, we just push a receive message to the message queue, which includes the pre-process and data transfer time estimation. The background thread will launch the empty kernel to preempt according to the switch overhead time before the data preparation stage stops. By doing so, the BE task throughput can be maximized. OK, let's come to the evaluation part. We evaluate GPREEMPT using two server machines with different GPU setup, one with NVIDIA A100 and another with AMD MI100, as the reset-based preemptive approach can only run on AMD GPUs. We compare GPREEMPT with the LC task-only baseline, which represents the ideal latency boundary, a non-preemption task representing the ideal throughput boundary, to weight-based preemption approach including sequential execution and block-level preemption, and the reset-based preemption baseline. First, we have DISP, which includes 6 typical DN inference workloads. And we have 2 synthetic workloads. Their LC tasks are DN computing, and the BE tasks are scientific computing and graph computing, respectively, which contains non-idempotent kernels. We first evaluate the latency of each approach. GPREEMPT and reset-based methods achieve very good latency on almost all workloads. However, for workloads Y and Z that contains non-idempotent kernels, GPREEMPT is still applicable while the reset-based fails. On average, GPREEMPT increases only 2.4% latency for LC tasks when collocating with BE tasks. For throughput, most methods can guarantee the throughput of LC tasks. For BE tasks, only GPREEMPT and reset-based methods maintain a throughput close to that of unscheduled tasks. On average, GPREEMPT ensures 88.6% of the ideal throughput. For technical analysis, we use workload A, change its data preparation time, and compare the increasing latency with running only the LC task. When the data preparation time reaches about 150 microseconds, the overhead caused by the switch can be almost covered, which shows the effectiveness of hint-based preemption. We also change the frequency of LC tasks and compare the throughput of BE tasks. The throughput of BE tasks decreases as the frequency of LC tasks increases. However, overall, the throughput of GPREEMPT is higher than that of the weight-based preemption method. After adopting scheduled pre-preemption, the throughput of BE tasks is further improved. Finally, I give a brief summary. In this work, our goal is to achieve a general and fast preemption approach. Our key idea is to leverage the context switch to preempt the BE tasks. We repurpose the time slice mechanism to a passive preemption mechanism. To further reduce the latency, we propose pre-preemption based on the GPU's computing paradigm. Evaluation shows that GPREEMPT achieves general while ensuring minimal increase in LC task delay. Although the GPU does not have a preemption interface, we indirectly repurpose the time slice into a preemption mechanism to achieve the preemption effect. Based on this work, we advocate for GPU vendors to expose a standardized interface, which would be a natural extension of existing internal mechanisms. We think bringing more operating system concepts to GPU make it more general and easier to use. Thank you for listening. If you have any questions, we encourage you to contact my colleague Ruwen by this email. Thank you.